This is a diagram representing competitive inhibition. In competitive inhibition, an inhibitor blocks the active site of an enzyme, which prevents substrates from binding to the enzyme. Inhibitors like sulfanilamide, shown in orange, is in the way of the substrate, para-aminobenzoic acid, shown in green. That is kind of like when you and your friends are trying to take a picture together, but a pedestrian passes by and photobombs.
This is a diagram representing non-competitive inhibition. In non-competitive inhibition, an inhibitor binds to an allosteric site on an enzyme and temporarily changes the shape of the active site, which prevents substrates from binding to it. For example, the amino acid alanine non-competitively inhibits the enzyme pyruvate kinase. In non-competitive inhibition, the inhibitor doesn't directly block the active site, but it indirectly stops reactions from taking place. This is like when you want to Snapchat someone in a crowded room, but you can't because you feel really awkward. In a metabolic pathway, a substrate is catalyzed by an enzyme, creating a product. The product of this reaction acts as a substrate which binds to a different enzyme, creating another different product. The product acts as a substrate for a different enzyme, and this pattern can continue on and on for a while. Each reaction changes the original substrate little by little. For example, the process of glycolysis utilizes the metabolic pathway, which controls the rate of product synthesis. An example of this would be baking a cake. Each person adds an ingredient in the process of baking a cake, and in the end, it results in a cake.
In end product inhibition, the end product inhibits the first enzyme by binding to the allosteric site of the first enzyme in the metabolic pathway. In doing so, the chain of reactions within the metabolic pathway stops until the inhibitor unbinds itself from the first enzyme and allows the chain to start again. For example, ATP acts as an end product inhibitor for the metabolic pathway utilized in glycolysis because it binds to the allosteric site of the first enzyme in the chain, which in this case is phosphofructokinase. When the concentration of end products gets really high, the chances of the end product inhibiting the first enzyme is higher. When the first enzyme is inhibited, the concentration will consequently get lower because the products get used up. So it's kind of a way to stabilize the creation of products. Going back to the cake analogy, think of it like this. The end product, the cake, is given to the first person in the cake baking chain of command. He gets food poisoning and he can't go back to work, so his team can't make more cakes until he gets better.